Question 5 is a big enthalpy question, and they throw an unfamiliar reaction at you straight away, equation 5.1. I don't think I've seen this one before. And they've also given you a table of data, and just make sure you're aware that they are enthalpy changes of formation. So the way I would tackle this, I would write the equation for the reaction we need to find the enthalpy change for across the top, and then a box at the bottom with elements written in. And what we're going to do is we're going to create a cycle by connecting the elements box with the species in the equation. So going from elements to 4 moles of this, well, the enthalpy change would be 4 times the plus 54. This enthalpy change of formation here, from elements to 1 mole of that, would be plus 54. We've got 4 in our cycle, so that's why we multiply by 4. So then you can see you've got 5 times the minus 20. And then we've got 4 times minus 394 for those 4 CO2s, and 12 times minus 242 for the 12 waters. Nitrogen is an element, and so therefore it doesn't have an enthalpy change of formation. It's 0, so we don't need to have an arrow there. Let's just explain the colours now. So this is Hess's law. We've got 2 routes going from elements to here. We can either go this way, the pink route, so that would be this enthalpy change plus this enthalpy change plus the unknown one is equal to the sum of the other enthalpy changes for the other route. So that's elements to the 4 CO2s, the 12 waters, and the 9 N2s. So you can see there, I've written that line across there, rearranged for the unknown, and then we solve for that, and we get minus 4596. Part B, we're given an enthalpy profile diagram for this equilibrium here. And I can see I've scribbled up there, it's endothermic. You can tell because the products line is higher than the reactants line. So let's have a look at what it's asking. Calculate the enthalpy change when 240 decimeters cubed of N2O gas measured at RTP is formed from N2 and O2. So the first thing I would be thinking is, well, this equation here is the formation of N2O, but it's the formation of 2 N2Os. And the enthalpy change for that is plus 164. So that's the first part. You can see I've written that there. And then the volume, what's that to do with? Well, the volume, you can work out the number of moles of N2O from the volume. That's 10 moles of gas. Remember, 1 mole of any gas is 24 dm cubed. So to make 24 dm cubed, that's 5 times what's in the diagram. And so it's going to be plus 820. What's the enthalpy change of formation for N2O? So it's testing your knowledge of the definition. Remember, enthalpy change of formation is the production of 1 mole of a substance from elements. And so there's the equation there. How does that compare with the equation in the diagram? It's half. So therefore, the answer would be half of 164. So it's plus 82. Same cycle again, or sorry, same diagram again. And this time we have to find out the activation energy for the reverse reaction. So we would be starting here and ending up there. So we would need to raise the energy of these 2 N2Os from here up to there. And so it's going to be the difference between these two numbers, which is 283. And then the final part of the question, describe and explain using equations how the concentration of ozone in the stratosphere is maintained. So this is testing your knowledge of how ozone is formed and broken down. So the broken down one first, O3 is broken down into O2 and O, but then the O and O2 can recombine and form O3. So how is the concentration of ozone maintained in the stratosphere? The rate of the green reaction is equal to the rate of the orange reaction. And then the final part of this question, write the two equations to show how NO catalyzes the breakdown of ozone. I'm sure this is on everybody's notes. So an NO molecule reacts with ozone and forms NO2 and O2. And then the NO2 that's formed in this step here combines with an oxygen atom and forms NO plus O2.